Hi, in this short video, I'm going to introduce the PSL embedded language of Plutus 2. PSL is short for Plutus Specification Language. As the name implies, it is a language used to construct specifications of scripts. What this means is that we describe the observable behaviors of the scripts, including the inputs, outputs, signatories, valid time range, etc. Let's first look at the data types that are important in our specification language. These data types mirror the respective types in PLC. P-integer is the integer type. P-value is the token value type. PUTXO is a UTXO, and PUTXO-ref is a reference that points to a UTXO. We also have token names, currency symbol, time range, pub key hash, address, and the byte string type. We also have the special p-own UTXO type. It describes a UTXO of the current script that we are describing. So its address is always the current script. We only have two fields, value and datum, that we can change. Finally, we have the p-data type. It is equivalent to the data type of PLC. The type that stores a specification is called a p-diagram. This is because we will be able to draw the specification as a literal visualized diagram with inputs pointing to the transaction and the transaction then pointing to the output. Diagrams are also a monoid, so you can combine these specifications into a larger one if needed. We have two recursive data types for now too, which is plist and pnat. They are just the list and natural number types that we are familiar with. Let's now look at the functions within the DSL. We can require an input via a UTXO-ref with required inputs. We can also link a UTXO-ref to a certain UTXO value with UTXO-ref is. Specifically, we can also require an input from our own script with an own UTXO via the require own input function. For outputs, we can either witness a UTXO output or create one. How are these two different? The difference is that creating an output requires the result UTXO to be unique, while witnessing doesn't have such a requirement. This can be used to avoid double spend attacks. For minting, we can also require a specific value to be minted if our script is a minting policy, that is. We can also require the transaction to mint values of other currency symbols with witness mint. Next, we can also specify other properties of a transaction. For example, signatures via require signature, and valid time range via require valid range. So until now, we haven't seen how to actually construct UTXOs besides own UTXO. It is via these two functions. With toAddress, we can construct a UTXO with a specific address, value, and datum. Or we can also construct them via toProtocol, which constructs a UTXO or specifies a UTXO from a script that satisfies a certain protocol or specification. These two words are used interchangeably rather than a specific address. Next, we'll see how to construct values. There is the empty value. And then there is make value, where we can construct an arbitrary value from any currency symbol. Can also make ADA values. And lastly, if we're a minting policy, we can make our own value. Then we'll see some examples. The most simple one is just a transaction that requires a signature. For example, this payment cases definition. It receives a pub key hash and returns a diagram. Diagram is just requiring this pub key hash as a signature. However, most scripts are more complicated. Let's see this counter cases specification. It looks pretty complicated, and most of the times we want to have a better way than reading the code to see the specification. And this is where the diagram generation functionality comes in, which is the major use case of PSL. We're able to generate a visualized diagram of the transaction specification. So here is a pretty diagram function that converts the term of a P diagram into a text. What does the text contain? It contains a mermaid code. Mermaid is a diagram language. So let's try calling it on this counter cases in GHCI. You can see this is the generated code. It is not exactly mermaid because it is a mix of case expressions and mermaid code. You can see that the script first does a case analysis on the redeemer. If the redeemer is counter step, then the specification is this, which is actual mermaid code. And we can copy this and generate the diagram. You can see that the output diagram is pretty clear. The yellow squares are all the UTXOs. And inside them, the hexagons contain the datum, and the double-stroked square contains the value. And it is very clear that the value x1, which is a variable, is not altered in the transaction, while the natural number in our counter is decreased by 1. Now, what about the other case that we have seen here, counter consume? We can copy this too. And we can see that it creates a new output at address x in the datum and locks the input value x2 here. Can also generate more complex diagrams than that. For example, my colleague has written a script that looks like this. And we are not going to go into the details here, but we are just going to generate the diagrams for it. We can see the mermaid code is quite a bit longer. We can also copy these to the mermaid interpreter. We can see that there are 2 outputs and 1 input. What about the other case? It has 2 inputs and an output. And here we can also see another feature of the PSL, which is symbolic evaluation. This transaction combines the inputs eta and eta prime into this new value in the output, eta plus eta prime. PSL is capable of this kind of symbolic evaluation, so we don't really need to enter specific values for the eta and eta prime to see the result. And this has been a short introduction to the PSL, the specking language, or PLC for now. Thank you.